In today's video, we'll explore networking our smart lamp controller, wiring it to a desktop computer using a simple Python script called SLCCmdr. In the last video, we modernized this old 1940s lamp using the smart lamp controller. The SLC board is like an Arduino board but with added hardware designed with lighting in mind. It includes a serial interface called RS-45. This type of serial interface can extend up to 4,000 feet and have up to 32 devices connected to it. What you're seeing here is SLCCmdr running disco party mode. This sends continuous commands to flash random colors and fades over a USB RS-45 interface here to the desk lamp. The cylinder lamp is running its own color changing mode at the same time. If you don't have an SLC board, you can use about any Arduino board together with an RS-45 shield or wiring a transceiver chip to an available UART port, which most Arduinos have. The shield or transceiver converts the voltage on the Arduino pins into a differential type signal for better noise immunity. You may have heard of the DMX 512 standard or DMX, which is used for stage lighting. This is also a type of RS-45 network. However, DMX is largely a one-way standard. Controllers mostly send data to lighting devices, though there are some exceptions. I came up with a simple bidirectional half-duplex protocol that is both simple and flexible and allows for future expansion. Bidirectional means you can send packets to devices on the network, but also receive responses, and devices can send packets on their own. Half-duplex means that devices can't both talk and listen at the same time, unlike Ethernet can, which uses two sets of wires. Bidirectional protocol becomes a lot more important when you're controlling more than lighting. Take an example of using an SLC board to control watering in your garden. Your computer or controller can send a valve on command, the water comes on. Then a few minutes later, your controller sends a valve off command. But what if that message fails to reach the device controlling the water? The SLC board has a feature where every command received will reply back with an acknowledgement. If your controller or computer does not see the acknowledgement, an alarm can be raised or commands can be resent. You have more confidence that the water will really get shut off. As to the wiring, some may wonder why bother with all these wires and just use Wi-Fi or Bluetooth instead. Yes, you can use boards like the ESP series, and they do make the communication part easier, but there are many situations where using a wired network is a better choice. Too many devices in one area could mean a noisy radio environment causing interference. If devices are far apart, there might not be adequate reception. Your communication could be picked up by others, or something or someone could also be transmitting something that interferes with your communications. And there have been news reports about lax security with some IoT devices. Using a wired network is less convenient, but it does eliminate these issues. It's good to reserve Wi-Fi and Bluetooth to nodes that really need them. With home automation, many devices are bolted down, so a wired network is a logical way to connect them. For the simplest type of RS-45 network, you'll need three things: a controller, a device to be controlled, and some twisted pair wire. A controller can be any RS-45 device. A desktop or laptop can be used if it's fitted with an RS-45 adapter. There are a variety of RS-45 to USB adapters available for less than $20. Here are some low-cost examples. For these tests, we'll use this one. This is our smart lamp controller. It is essentially an Arduino board with built-in RS-45 port, LED drivers, and an encoder. Any different Arduino type board can be used by adding an ADM4853 transceiver and a TVS diode pair. The wire can be common telephone or networking cable, known as UTP cable for unshielded twisted pair. Simpler telephone cross-connect wire can also work. It is important for it to be twisted because the electrical noise tends to be balanced because of the twists. That means less of the noise is actually picked up on the receiving end. For demos here, there are two SLC-controlled lamps connected to a computer using one of the USB adapters mentioned earlier. Each device has its own address. The lamp has address 25 and the vertical style lamp has address 32. This is how they're actually wired. The green terminal blocks have two sets of A, B, and ground terminals. The ground is normally not needed. More information on wiring RS-45 networks is on the page linked in the description section below. A terminating resistor is recommended at each end of the wire. The SLC boards have a built-in resistor connected by installing a jumper. If you add a new device, then of course remove the jumper and install it where the now last device is. There's interesting science to all of this. Without the terminating resistors, signal energy propagates to the end of the wire and then bounces back like ripples on a pond. This bounce back energy would interfere with the real signals. The resistor at the end acts like a damper, reducing the reflected energy. Anyway, this pattern can be repeated for up to 32 devices and a total length of 4,000 feet or 1,200 meters. Now that the physical part is complete, it's time to think about the softer side of things. On a small device like Arduino, there is no language or way to control it by sending data to its serial port. There needs to be some kind of interpreter running on the Arduino that will accept commands and take appropriate actions. With small controllers, it's best to create a command structure that's compact as possible, and also establish a structure that will handle as many future uses as possible. The SLC board comes pre-programmed with a simple protocol to control most functions. Each packet starts with a 1-byte fixed protocol identifier. This serves to validate received data as a valid packet. 3 codes are currently defined. One is for host-originated packets, hex A5, one for direct replies, A6, and one for remote-initiated packets that are not replies, which is A7. The second byte is the device address. Each device on an RS-485 network should normally have a unique address. Following the address is a third command byte, and this will vary depending on each device type. Some commands will require additional bytes, such as options or sub-resource numbers. The rest of the packet is defined by the type of command. Some will need more data bytes. Some of the commands and replies used in this video are shown here. For a complete list, follow the link below to the technical details. One note about data formatting. I find it helpful to think of the first bytes as hexadecimal. However, some data is best thought of as ASCII, such as Healthcheck replies. This is because hex is convenient for pattern matching and addressing. The replies to some packets like Healthcheck are things like times and dates given in ASCII. This makes it easier to read when using a terminal program when monitoring the serial data. Therefore, in the chart below, data is color-coded to show the encoding. Here are 3 examples. One is turning on an LED channel, one is a health check command, and finally the SLC reporting that the motion detector input has changed state. The health check command is a simple example. You can see the protocol identifier, destination address, and command byte. The SLC board set to address hex 19 will respond with the A6 start byte, the board's address, and then several values as an ASCII string. The date and time that the firmware was compiled, and some other useful stats, such as how many times the main loop has been run. Exact details may change from time to time, so follow the link in the description section for current reference details. There are many ways of communicating with an RS-45 network. The SLC commander script is intended to demonstrate some typical ways to interact with devices on the RS-45 network. Some commands can be sent with only command line options. The interactive mode can be used to send commands in real time, such as continuously dimming or changing colors. There is also a monitoring feature, so data being received can also be shown. SLC Commander is a simple Python 3 script used to exercise the features of the SLC board. It has an interactive mode that can be used to change the lighting channels using a computer keyboard. Many actions can also be done with the command line options, so SLC Commander can also be used in other scripts. It attempts to interpret some of the packets sent by the SLC board into a more human-friendly display. Here is the lamp from the last video on modernizing old fixtures. Follow the link below to watch how that was done. I put stickers on the lamps with their decimal addresses. That is used with the -A option you'll see below. The simplest way to show what the script can do is by using interactive mode with the -I option. This lets you send commands over the wire using your keyboard with single letters. We'll start We'll start SLCCmdr, the command line, and then we'll address the cylinder lamp, and then -I for interactive. To select a color, you can just press R, G, B, or W, and to change the brightness, use digits for percentage, 1 for 10% up to 9 for 90%. For example, I'll press R for red, then 4 for 40%, then 2 for 20%. Now I'll press G, and then 0, and then B, and 3. And we can brighten it up with W, and I'll press 6, and then I'll press 2, and then I'll press 0 to turn the white back off. The plus and minus keys will brighten or dim one step at a time. It's hard to see on camera, so I won't do that right here. You can also press Z to zero all 4 channels. SLCCmdr lets you send raw data to the network using command line options. This is useful for testing or experimenting. It is also useful if you want to make a command script to send a series of packets. I'll show you that in a minute. With this method, you have complete control over what is sent over the wire. The raw data can be sent using the -S option. The A5 protocol identifier and address is automatically added, followed by your hex data. For example, I want to set the cylinder lamp to a nice sunset color. We'll use the command 04 to set all the colors at once, and we'll use RGB value 200A00, and we'll leave the white channel off. We can use this command. This will set the red channel to 20, which is right there, the blue to 0A, which is right there. The green and white channels are off. And when I hit return, you see the result. I'm using the -Q option so we don't wait for any plies from the SLC board. That makes it faster. We can then set the desk lamp to a bright pale blue with this command. Just to show what you can do with these commands, I created a small shell script called controldemo. And so this is just a short script to show some ways of controlling the system with a shell script. And we can just run that with that. And it sleeps. And it turns on the backlight. And it turns on the other lights. And this is just in a loop changing the color gradually. You can see it's turning orange. And then it's done. We can tell the lamp controller to send back an acknowledgement with each packet it receives. In interactive mode, pressing A will turn this on and off. Typing A in interactive mode tells SLCCmdr to send a packet with the command byte 0xA1 to turn it on or off. Let's pretend the red channel is really a water valve supplying your garden. Before we start, we'll turn everything off with the Z. Now I can hit R and 1 to turn on the valve. And then I can press 0 to turn it off. The problem is, without seeing the red light, how do we know the channel really got shut off? Your water could be overflowing the plants right now. But we'll tell the SLC board to send back acknowledgements. So we hit A, and now you see the acknowledgement A6 packet. Now with each command to turn on the water on or off, we get a reply packet, so we know positively that the SLC board acted on the command. So when we press 1, we can press 0. Now see, this is what I'm talking about. The light did go off, but we saw no reply here. This allows the controlling script to know it should repeat the command. You can press 1, you can press 0. The SLC board automatically transmits over the RS-45 the events that happen on the local control. So if you push the button, you'll see it shows you what mode the unit is in. And if you turn the knob, you'll see the data showing the different states of the board. As your network grows and more devices are further away, you may want to have checks on them to be sure they're alive, and if it has been reset. The Healthcheck command makes this possible. When the Healthcheck command is sent, the SLC board replies with a number life count to indicate how long since the last boot and the time and date the firmware was compiled. The controller can send out Healthcheck commands, and seeing a continually increasing life count lets you know that the board has not lost power or been reset for any reason. The compile date is also useful if you have a number of devices on your network. They may all have been compiled at different times, and some features may only be present after certain dates. This is an easy way to be able to survey your network. And just for fun, there's a special option in SLCCmdr that changes the lights automatically. I call it the disco party. So on the command line, I'll add a $P for party. And what it does is it first sends values for about 10 different random colors, and then it does some ramps or fades, if you will, and then back to the beginning. It keeps repeating this pattern, and you can see the data that's being sent. I hope this gives you a good idea of all the things that you can do with the simple wired network and protocol. There are many other commands and options. I only showed a few to keep this short. Check the information below in the description to learn more.